Hi everyone, this is week 2 of the Intro to Statistics course. In this session we're going to look at relationships in the data, specifically correlations and scatter plots. Last week we looked at when distributions could differ between groups, but there are times when we want to know the relationships between one variable and another variable, especially if that relationship is strong. For example, knowing that we are seeing more older patients may help us plan for longer lengths of stay, and knowing the DXCG risk score could help us predict future hospital costs. And in this slide we're looking at the session overview. We will cover topics on correlations, scatter plots, and predictions and variance explained. We'll have examples for each of these topics. For correlations, we'll look at miles per gallon and horsepower. For scatter plots, we'll look at MPG and horsepower and the U.S. Department of Health's COVID-19 data. And for predictions and variance explained, we'll look at variables in the U.S. Department of Health's COVID-19 data. Correlations can tell us that low values in the first variable can lead to low values in the second variable, and high values in one can lead to high values in another variable. These are positive correlations, but we also have negative correlations in which high values in one variable are related to low values in another variable. We'll cover more of this in the following slides. Before we get going further, we'll cover a glossary of terms that I'll cover in this discussion. For example, a variable is any characteristics of an individual. A variable can take different values for different individuals. Variables can be categorical or quantitative, for example, gender and age. Variables can also give us an idea on a relationship, such as independent variables that lead to dependent variables. For example, high cholesterol can give us an idea about heart disease, and the number of patient visits could give us an idea about length of stay. The next term is significance. After selecting an alpha level, for example, 0.05, we check if correlations are sufficiently away from 0 to indicate they are unlikely to happen by chance. For example, when the correlation coefficient R equals negative 0.78 with a p-value less than 0.01, it indicates that there is less than a 1% chance of being wrong and rejecting the null hypothesis, that there is no correlation. We feel confident in saying there is a significant correlation. We then consider if it is a substantial correlation. So significance gives us an idea about what are the chances of us being wrong in what we are saying. The next term is an outlier. This is a value that we can calculate from the interquartile range, which we discussed last week. The formula is 1.5 times the interquartile, and we add that to the 75th percentile, and we subtract that from the 25th percentile. And values above and below that would indicate outliers. For example, outliers in miles per gallon are found below negative 4.3. This value doesn't exist, but this is the value that we would get from that formula that we just covered. Also, outliers are above the MPG of 33.1. We actually do have one outlier for a car with an MPG of 33.9. And for the next terms, we consider causation versus correlation versus confounding. Causation indicates a cause and effect path. Cause and effects can be correlated but correlations are not necessarily cause and effects. Confounders can be a third variable correlated with both causes and effects, and they can impact that relationship. For example, motivation can confound the correlation between math ability and SAT math scores. The more motivated a student is, the stronger the relationship we see between their math ability and SAT math scores. And conversely, the less motivated a student is, the less of a relationship we would see between math ability and SAT math scores. And the next term is a composite variable, and that is a constructed variable that is the mean of two highly correlated variables. For example, we'd have a correlation coefficient greater than or equal to 0.95, but we may also want to consider that value of 0.90. Generally on the same scale, so for example, airflow tests on different devices, they probably use the same range of values, and the HCAP score. And we consider composite variables because if you know two variables are highly correlated, it would be more efficient and less costly if you just collect information on one variable instead of two. So if I know one variable can give me the same understanding as two variables, then it's in my best interest to just collect that one item. But also, if you use that item, you can create a composite variable and reduce the effort in your analysis. So creating composite variables can help identify important things, but also could be easier in that analysis and that interpretation. And the last term in this glossary is reliability. It's often referred to as a correlation between two variables. For example, airflow test of different devices. If the alternative but less expensive device is highly correlated with the gold standard device, we would purchase the lower costing device. So if we see that my alternative device is consistently giving me airflow results as my gold standard device, then I can confidently go ahead and get the less expensive device. So just some general background on correlations. We have probably more than a dozen types of correlations. The Spearman correlations are basically the relationship in rank order of two variables. Other correlations use different formulas, but the general concept of showing relationships or associations between variables remains constant. So learning the Spearman correlation is a good way to understand how correlations work. The correlation coefficient R ranges from a value of -1 to a +1. Negative and positive correlations exist. A correlation coefficient of 0 indicates no correlation. We'll cover what negative and positive correlations are, but just it's important to know that ranges from -1 to a value of 1. And the following rules apply to positive correlation values, but have similar meanings for negative correlations as well. Some general guidelines in interpreting correlations are that the strength of correlations, for example, a correlation of 0.70 would be considered a strong correlation. Correlations that range from 0.30 to 0.70 is generally considered a moderate correlation. Correlations less than 0.30 are generally considered weak. and a correlation of 0 indicates that there is no correlation. And correlations of -1 or +1 are considered perfect correlations. It's important to consider how big your sample is, as well as how meaningful these correlations are. You might get a moderate correlation that is very useful to you and may have a greater importance than a value of 0.70. If we're considering reliability, a value of 0.80 would be very important. But if we're just looking at the relationship between two exploratory variables, you might get a value of a correlation value of 0.30 and be very happy with knowing that result. So we also need to consider the context of these correlations, but these are just some general guidelines of how we would judge the strength of correlations. So in this slide, we're going to look at how positive correlations are calculated. This is also just a good general idea of how correlations are calculated, but this set of data represents a perfect positive correlation. Notice the rank on your x variable, or your independent variable, or your predictor variable. The rank on that matches the rank in your outcome variable y. As one value goes up, the other value goes up. This is an example of a perfect positive correlation. So here are the rank on your predictor variables. In this case, it's height. We see for the values for these different subjects, the rank goes from 1 through 5. And when we look at their weight is also ranked in the same order, 1, 2, 3, 4, 5. And in this calculation, we have a difference of 0. And how this is calculated, that value of 0 is subtracted from 1. And we see that the correlation will give you a value of 1.0. So this can tell us as height goes up, so does weight. And in this next slide, we're looking at how negative correlations are calculated. It's the same type of calculation, but we're going to see what this looks like in terms of the rank on your independent variable and the rank on your outcome variable, or your dependent variable. For perfect negative correlations, the rank on x matches in the opposite rank in y. So they're in reverse order. As one value goes up, the other value goes down. So in this data, when we're looking at the rank on height, we see that the order goes by 1, 2, 3, 4, and 5 for these 5 different subjects. And when we look at their weight, we see that the rank's going in the opposite direction. 5, 4, 3, 2, 1. So in this data, we're seeing that as height goes up, weight goes down. And from that, we would get a negative correlation. So we have three types of correlations. We have a positive correlation that indicates as one value goes up, the other variable goes up. And we also have a negative correlation, which indicates that as one variable's values go up, the other variable's values go down. In this example, we looked at height and weight, and we looked at perfectly positive and negative correlations. There are special considerations when we use correlations. The first is that correlations are great small sample statistics. They're very helpful with large and small data sets. And for the second consideration, we need to think about how we can use it with aggregated data. Aggregated data can be helpful when there is at least 25 to 30 rows of data. Consider a correlation test for 2 to 3 years of monthly data. So what we can do in this situation is if you have 2 or 3 months of monthly data, you can also look at that trend over time. So for your month, you can, if it's coded as 1 through 24 for a 2-year period, or 1 through 36 for a 3-year period, you can then put next to it the aggregated value for each month, and you can get a correlation, and that correlation can tell you if that trend's going up or down. Oftentimes with some line graphs, it goes up and down, up and down, and it becomes difficult to identify that trend. Doing a correlation test can help give you an idea if that trend's going up or down over time. However, it is important to caution this use because aggregated data can mask variance and inflate the correlation coefficients. So, in other words, correlations could look better than they actually are. So if you're using aggregated data in your correlations, make sure just to consider what that trend would look like on in data that isn't aggregated, and just make sure to make note of that in your interpretations and your results. The next special consideration is R square, and in a correlation we get a value for R, and that correlation coefficient is represented by R. But if we square that, we get a special statistical quality, which gives us the idea of how much variance is explained in our relationship. So R square represents the amount of variance in Y, which is our dependent variable, that is explained by X, our independent variable. For example, when R equals negative 0.78 in the correlation between horsepower and MPG, the R square is then calculated as 0.60. The Pearson correlation gives the same R square that we get from a single linear regression. So in other words, when you do a correlation coefficient, specifically the Pearson correlation, that would give you the same understanding of the predictive power in that relationship that you would get from a regression model. So this could be helpful to do something similar to a regression, but in a faster way. The next consideration would be for the Pearson, Spearman, and Kendall-Tau correlations. These are good options to use for your correlations. You may want to use more than one for different purposes, but for these three, these three correlations can handle continuous, ordinal, and binary data. For a Pearson correlation, it works well. It works best when you have two continuous variables, but like the Spearman and Kendall-Tau, you can use it with different variable types. And last week we looked at the different levels of measurement, so that could refresh your understanding of those different levels of measurement. But for these three, they generally work well in all those situations. The Kendall-Tau works especially well in ordinal correlations. The Spearman works especially well in skewed data, and the Pearson is the fastest to calculate. So if you have a large data set, I would use a Pearson correlation. We're talking about tens of thousands of rows, or even 1,000 or more. You might want to just use a Pearson correlation. But when you're looking at your really big data sets, you'd probably want to. It's probably best to start with the Pearson correlation, and the Pearson also gives you that that R square value that matches a regression analysis. And for the next special consideration, we can consider partial correlations. They will allow you to control for other variables. So if you're looking at the correlation between horsepower and miles per gallon, but you want to consider the number of cylinders in a car, you can do that in a partial correlation. But we get more power by doing that in a regression, and that may be the better way to go. In this next section, we're going to look at examples. We'll look at scatter plots with correlation test, as well as a correlation matrix and using it to set up studies. In this slide, we are looking at a negative and strong correlation. We're looking at the correlation between horsepower and miles per gallon. It may be difficult to see these little dots that represent data points. So, for example, at this one dot on the far left, we see that a car with 60 horsepower gets about 25 miles per gallon. And so these coordinates, these values also represent coordinates in this graph. So a value of 60 horsepower lines up with about 24 or 25 miles per gallon. So we have data that represents that, and it's indicated by this circle that we have in the graph. And we also have a purple dashed line. This purple dashed line is a lowest trend line or a low smooth line. It's not what you would get from a regression model, but it has a similar idea where it shows the trend that you have between these two variables. So in our relationship between horsepower and miles per gallon, we can see that this purple dashed line is about in the middle of where these dots would line up. And so that gives us an overall average of that trend. So in this example, the Pearson correlation coefficient of R is negative 0.78, and it is significant with the p-value of less than 0.001. There's a very low chance that we'd be wrong in saying that there is a strong relationship between horsepower and miles per gallon. In other words, we're safe saying that higher horsepowers can lower your miles per gallon. And from the correlation test output, we can calculate the R square of 0.60, which indicates that knowing a car's horsepower gives us a good idea of what the expected MPG is. In other words, horsepower explains 60% of the variance in MPG scores. So on this one circle, with this one red circle, we see that's the correlation. We square that, and that gives us the R square of 0.60. And this other red circle has the p-value, and we see that's a very low p-value. And so we see in this data set the n, or the sample size, is 32. So if you're working with 2 or 3 years data from a dashboard, that's about the same sample size. So you can get a meaningful interpretation, although you'd want to caution your audience that you're with the issue of aggregated data, but you can get this type of analysis and make it useful for you in different ways. An important thing to point out is how we set up a correlation graph or a scatter plot. For the y-axis, it's generally what we use for outcomes, and the x-axis is often for predictor values. If you're doing exploratory work and you just have two predictors and you want to see how they might be related or associated, You can just enter these in any pattern. But if you do sense, or you do consider that you're looking at a causal path or a predictive path, you would put your outcome on the y-axis, such as MPG here on this y-axis, and you would place your predictor or your independent variable on the x-axis, and that's the general format with scatter plots. And in this example, we're looking at a positive and a moderate correlation. We see that for the percent of inpatients with COVID, that there's a significant but maybe a moderate correlation that it has with COVID deaths. On the y-axis, we have our outcome of deaths from COVID, and on our x-axis, we have the percent of inpatients that had COVID. So the relationship we'd want to look at is if the pattern that we see when based on the percent of inpatients with COVID and how that relates to the number of COVID deaths. In other words, do we see more COVID deaths because of our high COVID volumes? The Pearson correlation is 0.29, but we see circle up top outliers, and with the Pearson correlation it's a little bit more susceptible to outliers. So we look at the Kendall and Spearman correlations. Those are both moderate values at 0.47 and 0.63. So probably for taking into consideration the three values, we'd probably want to consider this a moderate correlation. It's close to that for the Pearson correlation, but when we look at other correlations that are helpful and with skewed data, or when we have a lot of outliers, it's probably safe to call this a moderate correlation. The R-square that we can calculate from the Pearson correlation is helpful in stating that the correlation is significant, and the percent of inpatients with COVID explains 8% of the variance in COVID deaths. It's an important predictor of deaths, but there's still other important factors that remain. And in this next graph, we're going to look again at the percent of inpatients with COVID and how that may predict COVID deaths. These are trend lines. So we have a third factor on region. So we have 6 regions in the US. And we can see how what the relationship is between percent of inpatients with COVID and COVID deaths for each of these 6 different regions. These lowest trend lines are descriptive only. They are similar to the scatter plots above, but have multiple lines for each level in the region factor. There are no data points nor correlation tests. Values at the top are percentiles of the x-axis variable. This is something that I have in my Shiny app, or my GUI. And this can let you look at more than one relationship at a time and compare with the various levels in that factor. And from it, we see the number of deaths is most strongly associated with the percent of inpatients with COVID in eastern states. The North had the worst mortality as it spread there first. So we look towards the bottom right in this graph, and we see this green line, which represents the North. So because the pandemic started there first, we see that as hospital volumes increased with COVID patients, the number of deaths increased. And we can also we may also consider that the lower rates in the West may have been partially due to better understanding in how to treat COVID by time it reached the West in high numbers. So this one trend line on the bottom in purple, that represents what we're seeing in the West, in the Western states. And then in this one group in the middle, we see the Midwest, South, and Southwest. So their values are higher than what we see in the West and even in the Northeast, but what we saw in the northern states such as New York and New Jersey looks to be a lot different. So another benefit of looking at this data this way is that we can now, as we start to consider what things to look at, because we're starting to see a distinct pattern, we may want to consider region in future analyses. And an important note to make is that the more levels we use, the more data is required for each of those levels. We have probably over 25,000 rows of data in this data set, so we can look at data for all 50 states, but just kind of what we've been seeing and what we know with COVID is that we do see different things month to month. Some months are more consistent with each other, but we've seen COVID cases go up and down, and we've also had different treatment plans and different options to nullify the effects of the or minimize the effects of COVID, such as our vaccine and our different treatments, and just generally with the better understanding of COVID, we're helping to improve mortality. So with this, we know time's important. So if we split up the data based on state and then separate it by time, we get less and less power in each of these levels for each of these different time points. So for this, I'm just looking at regions. And because we're looking at time, I may continue to look at it this way. So in this next slide, we're looking at a correlation matrix. And a correlation matrix is very helpful at identifying which variables are closely related to the outcome and which variables may be redundant in your analysis. So a correlation matrix is just a set of rows and columns, and each row represents one variable, and each column represents the identical variable, and we can see how each of these different relationship lines up, and it gives us an idea of which ones are going to be the best or which ones potentially could be the best predictors of your outcome, and which variables are highly correlated. We do have to consider which variables are redundant. In other words, like a composite or highly correlated data, we may consider that for things that are highly correlated, we may not want to use both of them. If you're doing a regression, when you have two highly correlated variables, your regression is going to want to throw them out because there's a loss of power in having two things that are almost identical in the same analysis. And we'd also want to consider that in general when we're using a correlation matrix. So in this first column, we see the number of deaths from COVID. We see that one of the strongest correlations with COVID deaths is the percent of inpatients with COVID. And so that's very similar to the inpatient bed COVID utilization variable. They both just give you an idea of how many people are in your hospital with COVID. And when we look at the inpatient COVID utilization, we scroll across, and we're going to look for that percent of inpatients with COVID column, which shows up here on the second column from the end. We see that that correlation is 0.97 or 0.969 in this output. So that's really high. We see that they're pretty much almost identical because they're so highly correlated. To make our analysis more efficient and also to give it more power in other studies, we should consider removing this one of these two variables from the analysis. And when we go down a row and we go to the percent of inpatients with COVID, we scroll across and we look for that second variable in that relationship, and that's the third column from the end. So both of these values that are circled in red represent the relationship between inpatient bed COVID utilization and percent of inpatients with COVID. It's just part of a correlation matrix that each of these relationships gets represented twice. So if we wanted to, everything above that value of 1, we can just ignore. That value of 1 actually represents a perfect correlation and represents a correlation between each variable. So we see on the very top left in the correlation matrix, we have a value of 1.0, and that's the correlation between COVID deaths and the correlation between COVID deaths. The second value in that diagonal would be critical staffing shortages, today yes, and critical staffing shortages, today yes. We can also ignore the values of 1. That just means that the value is perfectly correlated with itself. So everything below that diagonal we can consider as our main correlation and ignore everything above and at that diagonal. So that's why we have this identical value of 0.969. We're seeing it twice because that relationship is by default listed twice. So because we know this is highly correlated, and it may just be better and at least easier, we can ignore one of these two variables. I've just used percent of inpatients with COVID. It's not perfectly correlated, so we do see that it's actually a little bit lower than that inpatient bed COVID utilization, and that correlation is 0.309, and that correlation represents that the relationship between the inpatient bed utilization and COVID deaths. So we can make an argument for using inpatient bed COVID utilization rather than the percent of inpatients with COVID. But we've just been using this one, so we're just going to go ahead and use it. But we can also see that critical staffing shortages also appears to be a significant correlation with COVID deaths. And then we can see that hospital onset COVID is actually one of the weaker correlations, but it may offer some sort of information that we're not getting from these other variables. These other variables seem like they would be correlated, and we can see that in our correlation matrix. But we might have some unique information that's found within this correlation between COVID deaths and hospital onset of COVID. We also have month in that correlation matrix. It's a weak and negative correlation, but we can use weak correlations if they represent a unique part of the puzzle that we won't get from any of the other variables. So we'll go ahead and use month as well. And For this, we're identifying which things we can use in a study. I'm going to use what we learned here as part of a regression analysis. And here's a variable importance plot and the results from a regression. We see that if we were to rank which things had the most importance, it would be the critical staffing shortage today variable. If we go back, we see that correlation was 0.265. The correlation for percent of inpatients with COVID was 0.297, so at first I would have thought that would have been the variable that would have shown up as most important. But there probably is the correlation that it had with other variables probably weakened it after taking into consideration those other variables. So critical staffing shortages probably stood out more on its own, while the percent of inpatients with COVID probably had a greater relationship with these other variables than did the critical staffing shortage. But they're both very important and they're very similar, so these variables are definitely things we'd want to consider. We see for region, that's the next most important variable. And we did see those trends in the earlier slides that showed a distinct pattern between our different regions. So although it wasn't the strongest correlation, actually I don't have it there, but it wasn't the strongest correlation, it still added quite a bit of information. And region, like all the other variables in here, was statistically significant. We also saw that month was a strong predictor. We know that there was a trend or a relationship between COVID deaths and month. It probably looks a little bit more important here because it offered a unique set of information that we didn't get from the other variables. And for the least important variable, but still very statistically significant, we see the hospital onset of COVID. That indicator was also an important predictor, but in how it ranked, it was the least important variable here. So the model R was bigger than the strongest variable in the correlation matrix, and we see our model results here that this corresponds to a correlation coefficient. That value is 0.37 or 0.37. We see of the variables that we used, the biggest was about 0.30. So we see that this regression model gives us a little bit more information than the correlation coefficient, but if you're not able to get access to regression results, you can get a pretty good idea of what predicts your COVID deaths based on that percent of inpatients with COVID. So that is about on the, I used Pearson correlations, and that by itself is about would round up to a moderate correlation. And if we use Spearman correlations or Kendall-Tau correlations, we would see that it would be a moderate correlation. And that's what we did here. We're looking at percent of inpatients with COVID and COVID deaths. So we see that from this analysis that's a moderate correlation. And what you might be left considering is that you can probably get something similar to this regression model based on picking the right variables or the right variable that's correlated with your COVID deaths outcome. This regression model does give you a bigger R, and when you calculate the R-square, you see that about 14% of the scores or the values for COVID deaths are explained by this model, which is not that far off from that single predictor. And if you know that with the range of weak, strong, or moderate correlations is at, that can give you an idea, that can give you insight of how important that predictor is and about how predictive it is. Because of significant correlations between variables, the R-square isn't closer to the sum in the correlation matrix. For this, we can't simply add up these correlations for these bottom 5 rows. If they were all uniquely different, that adding them up probably would give us a good estimate on the overall R-square. But since we see in this correlation many of these things are are significantly correlated, that we'd have to rule out some of their impact in getting that total R-square. However, we can identify important predictors from the matrix and identify which variables would have the most impact in understanding results. So in this session we covered correlations, scatter plots, predictions, and variance explained. If we have an idea what that relationship is, we can use the correlation line to give us an idea on what our predicted values might look like. In other words, you can use this line to make a prediction. If you know that the horsepower is about 100, you can then guess that the miles per gallon could be about 23 miles per gallon. And you can also use that to assess another person's prediction. For example, if they have a 250 horsepower car and they say that gas mileage is about 30 miles per gallon, you can use correlations in a scatter plot to know that prediction is probably incorrect. So again, we looked at correlations, scatter plots, predictions, and variance explained, and that can give us an idea of the strength in relationships and our understanding of it. We should have week 3 soon. Thank you.